These last two sections of chapter 11, 11.10, 11.11, they take our idea of the power series and we look at it as a Taylor and Maclaurin series, as you see the title of 11.10. So can just kind of give you the what's going to happen. So a power series, we can represent certain functions in this style as an infinite series. But we're pretty limited on where we left it in 11.8 and really 11.9 when we were using the geometric series to write things in the form of a power series, right? So it turns out there's a much more general approach that we can approximate many more functions as a power series. We're not stuck with things that just look like the outcome for a geometric series. And you may find that once you get the hang of it, that it's actually easier than the way we did things in 11.9, maybe. So here we go. I've written this again since we're building on this idea. The power series of f of x centered at c takes this form, n equals 0 to infinity a n x minus c to the n. Now what really changes from power series to power series is the an, right? What's the coefficient look like here? Is it just a constant? Does it contain the variable x as well? But we always have x minus c to the n, and typically we start at 0, although you don't have to. Approximates f of x for x values that can converge. One thing to remember in all these, it's not true in general, it's only true for the x values that cause your infinite series to converge. The further you get away from c, then you might start to diverge if you get out of your radius of convergence. Okay, so at this point we've got a theorem, and we will explore this. We'll prove it, in fact, and that will even help us out. The proof even helps us when we get to problems. Okay, so it says if f of x, our function, is equal to the power series for x values that cause this to be true, in other words, your value of x converges because you're inside your radius, then that coefficient, the thing that really is what is in question, turns out to fit this pattern. That's the nth derivative of f evaluated at c over n factorial. So the nth term is the nth derivative evaluated where you're centering over n factorial. It's like, okay, that's strange. We're connecting this with derivatives now. Yeah, okay, so let's explore this theorem, and we can prove it to ourselves without a whole lot of work. So here we go. So I'm just going to show you what would f of x look like, right? So we've got we're defining f of x as equal to this power series. So f of x, let's expand that. Let's think of several terms added together. So if we take the 0 term, right, that's a0 raised to the 0 power. Well, to the 0 power is just a0. N equals 1, well, that's a1, and we raise to the first power, right? The second term, well, that's a2 to the second power. The third term is a3 to the third power, and so on. Okay. And so, of course, the question is, what's going on with the coefficients? Okay. Now, our an involves derivatives. So I'm going to take a few derivatives here, and then we'll explore the centered at c part. The first derivative of f of x, hey, if I take the derivative, well, that's a constant with respect to x, right? So that would be gone. So then we would just have this derivative is 1, so we just have a1. Here the 2 would come down, right? Here the 3 would come down, drop to a square. There's our first derivative. The second derivative, well, now our a1 is gone. That derivative is 1, so we just get this. Here the 2 multiplies down, you know, and so on. I'm even going to go one more just because we've got the terms for it the way it's laid out. So the third derivative, well, now that goes to 0. That's 1. Okay. One thing that came to mind, you might not have had this question as I was walking through this. I mentioned a moment ago, sometimes the an, we're used to seeing it involving x. Sometimes our coefficient here involves the variable x. We saw that in 11.9. But here I'm treating it like it's just a constant when I'm taking these derivatives. Because of the way that this is defined, well, that's a constant, right? A function evaluated at a value over another number. That's always going to be a constant. So here I can treat my a's as a constant. Okay. So we haven't gotten there yet. What we're going to do is plug in c into each of our derivatives. All right. And hopefully we can fit the important part on the screen. So if I look at my function, my original function, and I plug in c, okay, plugging in c, well, plug in c there gives me 0, 0. All these terms and so on would all go to 0 because they've got c minus c. So all I'd be left with is whatever that number is, a0. Okay, okay, you can kind of see what's going to happen. What happens when we plug c into the first derivative? Well, that's going to become 0 when I plug in c and all that, so I'm just going to have a1. Think of a1 almost like, think of this as over 1 factorial. You know, we can get it to fit the pattern. How about that second derivative? Well, same idea. If I plug in c for x, well, that's going to be 0 right there. So all I have is 2a2. Aha, think of this. Divide the 2 this direction, and 2 is 2 factorial. Okay. And finally, the third derivative, well, all of these values would have an x minus c component, so they would all go to 0 when you evaluate at c, so it would just be 6a3. Divide that 6 over, isn't that over 3 factorial? And even a0, I should have written it there too. This is the original function over 0 factorial. Since 0 factorial is equal to 1. So that first coefficient, a0, is the 0th derivative over 0 factorial. That first coefficient is the first derivative over 1 factorial. Right? a2, the second derivative over 2, a3, the third derivative at c over 3 factorial. And we've done it. The nth coefficient is the nth derivative evaluated at c over n factorial. And we can see that pattern would continue with more derivatives, right? Okay. Well, let's put this into practice and define the Taylor series for f of x centered at c. All we're going to do is really do the natural next step to that theorem, is plug in what we know the nth coefficient to be, the nth derivative of your function evaluated at c over n factorial. F of x will equal the power series with that coefficient x minus c to the n. It's not written, but we assume this is only equal for values of x that converge. What's important, of course, is that coefficient. Okay. Also, at the same time, let's define the Maclaurin series. So it turns out the Maclaurin series is just a special case of the Taylor series. If you happen to be centering at 0, then we don't call it the Taylor series, we call it the Maclaurin series. And if you're like me and like a lot of people, you're like, wait, what? That's it? Who is this person Maclaurin who gets this claim? Like the simplest case of the Taylor series, we give it this whole new name, you know, after this other person. Yeah, I really don't know the details of the story. I know a little bit about Taylor, and I mean, he obviously worked with Maclaurin. I don't understand the history. Maybe Maclaurin discovered the centered at zero first, and then Taylor expanded upon that. And that's why his name gets put to this one, although this is the more general form, you know. I'm not really sure. I do think it's strange. Like, wait a second, like, just a one easy case. Anyway, it doesn't matter. It's really all the same, right? It just, if you happen to be centering at zero, we call it the Maclaurin series. Later on, you may see it, have seen already near the links to the videos. There will be a handout that you'll need for some of our last couple of examples on a big list of Maclaurin series. So I'm not going to speak to that handout yet. It's going to be toward the end of the lecture. And then I'll tell you, okay, go ahead, bring that thing up, maybe print it. It's in your textbook as well. We're going to start with more general cases, and then we're going to come back to what's going on that handout. Okay, I probably said too much about it. Let's stop the first video here. We will do a couple of examples in the next video exploring Taylor and Maclaurin series.